introduce.
I hope my screen is visible, sir.
Yes.
Good morning, good afternoon, and good evening to one and all present here. I welcome you all to the 7th lecture of our COE lecture series on molecular materials and functions. Today's speaker is Professor Umesh V. Waghmare, a renowned scientist in the field of material science. Professor Umesh completed his BTech from Department of Engineering Physics from IIT Bombay, India in 1990, and then pursued his MS MPhil in Applied Physics from Yale University, United States, and a PhD in Applied Physics from Yale University, United States. Then he continued to his postdoctoral research in Physics Department, Harvard University, and became a research associate there till 2000. Then he was appointed as Assistant Professor in Theoretical Sciences Unit, JNCASR, India, and was promoted to Associate Professor. And now he's a professor at JNCASR in Theoretical Sciences Unit. He also has served as adjunct professor from 2010 to 2012 in Berg Nanotechnology Center, Purdue University. And from 2014 to present, he is an adjunct professor in Tata Institute of Fundamental Research, Mumbai, India. His research interests include materials for energy and environment, multiferroics, and dilute magnetic semiconductors, nanoscale materials, among others. He has over 450 plus papers with more than 34,000 citations with a H index of 73. He has been awarded many awards, among which some of them are DuPont Young Faculty Grant Award 2004, MRSI Medal of the Year 2005, BM Birla Science Prize in Physics 2005, Fellow of Indian Academy of Sciences, Bangalore 2008, Shanti Swarup Bhatnagar Prize in Physical Sciences, CSR, India 2010, Infosys Science Prize, Engineering and Computer Science 2015, CNR Rao Prize Lecture, Materials Research Society of India 2016, Distinguished Alumnus Award, IIT Bombay 2017, GD Birla Award for Scientific Research, KK Birla Foundation 2016. Today, the topic of today's lecture is Theory of Structural Phase Transition in Crystals. Over to you, sir. Thank you.
Thank you, Amok. I will share my screen. First of all, special thanks to Amok for keeping up with my change in the schedule and being patient with me. It's a pleasure to be here in this gathering. Can you see my screen?
Yes.
Yeah. Okay. Wonderful. And I'll just. Okay. You can see my slides now, right?
Yeah. Absolutely.
Yeah. So it's really a pleasure to be here with you all and share with you some of our ideas and related work. So first of all, most of the materials in this talk will be hard materials. And in that sense, you would wonder why I'm choosing this topic for the audience in molecular materials and functionality. So one important thing is in hard materials where the functional materials have been extensively studied, phase transitions play a very important role in emergence of functionality itself. So I think there is a lot to learn from this domain of material science and use these ideas in molecular materials as well. And I think that sort of is the concept that we will learn from ideas in this area of hard materials and see how they may translate to soft or molecular materials. So let me get started. So materials behavior is strongly determined by the structure, and there is a fundamental paradigm, structural properties paradigm in material science, which most of us try to uncover and understand from fundamental point of view. And naturally, structural phase transitions, which involve a sudden change in the structure, possibly involving breaking of the symmetry of the material, is quite fascinating because it gives rise to emergence of new properties. And also near the phase transition, there are very large responses. Material, because of the fluctuations at the phase transition, material tends to be very sensitive and they respond to symmetry breaking fields in a very sort of colossal way. So you not only have new functionality and technologies, but also you have fundamental science of phase transitions there. And I will try to illustrate these ideas using, one second, the examples from our work. First one will be on ferroelectric phase transitions, which involve breaking of inversion symmetry, and that gives rise to the functionality of piezoelectrics. Secondly is martensitic phase transition, which involves breaking of translational symmetry, and shape memory effect is a result of that. Next is Nile phase transition in yttrium magnetite, which involves breaking of time reversal symmetry and gives rise to magnetoelectric effects. And amorphization of MOF5, which basically is associated with the porosity and also hence the catalytic surface area of these materials. And lastly, this is all provided the time permits, is the structural transition in high entropy alloys, which is relevant to their mechanical strength and toughness. So let me first convince you why structural phase transitions are so important. And in fact, they're so important that they play a role of kind of design parameter in thinking about new materials. So example here is of a ferroelectric phase transition, and a particular material is barium titanate or lead titanate, which occurs in the cubic perovskite structure at high temperature. It's a very beautiful structure. The barium cation at the corner of the cube and titanium cation at the center of this oxygen octahedron. Okay, and as you lower the temperature at a transition temperature T0, this crystal suddenly breaks inversion symmetry, and this breaking of symmetry arises from or is associated with off-centering of this titanium atom from its central position. And once it's a positive ion which gets off-centered with respect to negative oxygen ion, you develop an electric dipole moment at below the transition temperature. Okay, and the symmetry allows this dipole moment naturally to distort the crystalline lattice to a tetragonal shape, giving strain as reflected in non-trivial C by A ratio. Okay, so this phase, the low temperature phase of barium titanate, which is a very important functional material, is the only one which has new functional properties like linear piezoelectricity or non-linear hysteresis in polarization, which gives rise to applications which basically like, one second, let's see if I can. Applications like sensors and actuators. The speakers in your mobile phones are based on the same principle, and also non-volatile computer memories, which basically are linked with the switchable polarization as reflected in the hysteresis. So this is a very simple example of how phase, in particular structural phase transition, governs the properties of the low temperature phase. And near the transition, of course, the dielectric and piezoelectric responses are very colossal, which are relevant to the applications. The second example I'll like to give is martensitic phase transformation. And this is in a very sort of prototypical material called nickel titanium. At high temperature, this material occurs in a sort of cesium chloride-like structure where nickel is on the cubic lattice and titanium is at the center of that lattice. But as you lower the temperature, it reduces the symmetry of this lattice by deformation, which involves change in the lattice constants and significant changes in the lattice constant, and also the internal positions of atoms, which break translational symmetry. And as a result, you get this low temperature phase called martensitic phase, which has a new functionality like shape memory effect. Okay, and these effects are relevant to use of these materials in actuators, smart structure, and so on. So this is another example where a phase transition governs the properties which are relevant to real world applications, and particularly of technologies. So how do we think about these phase transitions? Well, they involve very interesting science. So here I'm showing you energy as a function of U parameter. U is the displacement of this titanium atom in barium titanate, for instance, from its centrosymmetric position. And that centrosymmetric position corresponds to this point, U equal to 0. That's the cubic perovskite structure. And as you distort titanium atom out or off-center it, the energy of the lattice reduces. This is energy, by the way, calculated within first principles, density functional theoretical framework, and you get lowering of energy like this, and it settles in one energy well. Of course, if you flip this direction of off-centering, you will get the another energy well here corresponding to negative dipole moment. And likewise, in fact, there are many other symmetry equivalent energy wells associated. What is spectacular is typically these off-centering displacements in these oxides are of the order of 0.3 angstrom. And the total energies of these crystals are 10,000s of electron volt typically. And this energy difference is very tiny, just 10 milli eV per formula unit. Okay, so you're looking at very tiny energy differences between two large energies that can be calculated from first principles. So you do need very accurate first principles calculation to capture such a phase transition. But this is the figure. Now I'm going to take this opportunity to explain another very fundamental aspect of these structural phase transitions, namely that in the high temperature phase, which is the cubic phase, the maximum of this energy well, since it's a local maximum, its second derivative of energy with respect to U is negative. And what this means is this cubic structure has an unstable phonon mode because second derivative is related to the spring constant of bonds, in this case, the off-centering of titanium atom, and that results in unstable vibration, at low temperatures. On the other hand, if at low temperature the crystal settles into this low energy phase, this energy here it's a local minimum, and as a result, the second derivative of total energy is positive, and that means the structure is locally stable. Okay, so the key message is vibration, or what we call phonon, is involved in this phase transition, and the phonon, there is a concept of unstable phonon which I highlighted from this little cartoon picture. Now, if you think about a phase transition in this framework, and what I'm showing you is the frequency squared of a phonon of the cubic phase, which is unstable at low temperature. You see at high temperature, the phonon frequency drops very close to zero. This is called soft phonon near the transition temperature. In fact, the concept of soft phonon originates from Bangalore as well. In the C.V. Raman in 1939 talked about this in quartz phase transition, alpha to beta phase transition in quartz. And as you lower the temperature, well, cubic phase cannot be stable, because if necessary, this phonon would have become square would have been negative, and you get a local maximum of energy. And this is the frequency that I showed you on the last slide is negative. Okay, this one. So this is how it looks like. But in real world, at below TC, the material stabilizes in tetragonal phase, and in fact, this phonon splits and becomes two hard phonons or stable phonons in the tetragonal phase, and that's reflected in the second derivative being positive for the tetragonal phase. Okay, so this is sort of is the fundamental picture of structural phase transitions, which are phonon-related phase transitions. Meaning, in these specific class of structural phase transitions, we are not going to talk about diffusion of atoms, which involve displacements of atoms from one unit cell to next or further. Instead, atoms are displacing within a unit cell, lowering the symmetry, and these are called as displacive, or also in some instances order disorder phase transitions in the crystals. Okay, so this cubic structure is unstable at low temperatures. So let me summarize what the scientific challenges are in the theory of structural transitions in crystals. First of all, you do need first principles density functional theory, because, for example, if you take barium titanate, it has very mixed type of bonding, which involves covalency, ionicity, and also pp interactions between d and p orbitals of titanium and oxygen. And the material specific properties are to be predicted. You don't have any other option but to use first principles density functional theory at present. And this is the only theory which can capture the small energy differences between very large energies of high and low temperature structures. I'll come to this point within a few slides, by the way, because this is still a challenge for standard density functional theories. The second is these phase transitions are dependent on temperature. So here, the quasi-harmonic approximation of phonons is not quite valid. So phonons are highly anharmonic, and that's actually what is reflected in the double well energy function. And that means the nonlinear phonon-phonon or phonon spin interactions can be very strong. And you need basically molecular dynamics or Monte Carlo simulations to study such as thermodynamics of such a strongly anharmonic system. Unfortunately, you can combine ab initio or first principles with MD, but then a phase transition occurs strictly in the large size limit. And there, these simulations are very impractical, because to do ab initio MD for thousands of tens of thousands of atoms is computationally too expensive. Okay, so these, in the background of these challenges, the approach that my group takes is basically called as the multi-scale modeling strategy, where we start with first principles calculations, where we have access to the full space of phonons, but only length scales of 1 to 2 nanometers. And then we use the technique of coarse graining in time domain and integrate out all the high energy phonons from the system, and basically arrive at a subset of phonons for which we develop a model Hamiltonian, which can be simulated in molecular dynamics and allow us to access 10 to 20 nanometers of length scale. And with this, we can predict phase transitions and phase diagrams. But this is not still enough to access modeling of devices or technologies based on these materials. So we take the next step, where we do coarse graining in real space domain. And basically the technique we use is called polostat, like thermostat, and thermodynamic integration combination, which allows us to derive Landau theory or Landau-Ginzburg theory, free energy functional from first principles essentially. And that allows us to now simulate devices on the scale of hundreds of nanometers. And at the same time, we derive fundamental understanding of phase transitions, as well as get simulation ability or capability of simulating devices based on these systems. So let me start with the first example in our work, namely the ferroelectric phase transition behavior in the two oxides, lead and barium titanate. You see that only one cation is changing, lead or this barium. And in fact, titanium is the sort of strongly active ferroelectric cation. But you will see that the behavior of these two oxides is quite different. And this is what we capture from our simulation. So the first step in modeling is basically start from first principles and develop a model Hamiltonian. So I'll just give you a flavor of how this is done. So using first principles density functional theory, we determine what is called as phonon dispersion. This is phonon frequency as a function of wave vector in the Brillouin zone of the cubic structure. You see the cubic structure is unstable at 0 temperature. So naturally what we see here, these are negative phonon frequencies, but they are actually imaginary phonon frequencies. And these are the unstable phonons that I introduced to you initially. Okay, so first principles calculations give us very precise access to all the lattice instabilities of a crystal. This tells you that, well, at gamma point is basically the wave vector equal to 0, 0, 0, and these are other high symmetry directions and points in the Brillouin zone. And at R point, all phonons are stable in barium titanate. But in lead titanate, you will see the situation is very different. You have unstable phonons all across the Brillouin zone. Yeah, and that means the lattice instabilities of these two materials have qualitative difference with respect to each other. I remind you that these phonons in blue, these are high energy phonons, and their energy well associated with off-centering of these vibrations or atomic displacements is a single energy well. And that type of energy well you can integrate out from your thermodynamic statistical mechanics analytically. And on the other hand, the phonons in this red dash boxes are unstable. These are the lowest energy phonons. And for them, the energy well associated with atomic off-centering is a double well function that I introduced to you earlier. And these we cannot analytically integrate out of the statistical mechanics partition function. So idea is to develop a model Hamiltonian by integrating out these high energy phonons, and then the model is basically focusing on the phonons inside these red dash boxes, which involve unstable phonons as well as acoustic phonon branches here, which basically gives you the lattice distortion or deformation. Same here in lead titanate as well. So effective model Hamiltonian is projection of the full lattice Hamiltonian of the system into the subspace of these unstable phonons. Okay, that's the first sort of principle we use in modeling, and this is basically the coarse graining in time domain, because we are integrating out high frequency phonons, which means the short time scales are not so important in the phase transitions. We then use this model Hamiltonian in a code which we developed along with few collaborating groups, one from Japan in Tohoku University and also Rutgers in United States. It's an open source software where we can use such models, Hamiltonians, and do molecular dynamics simulations of ferroelectric phase transitions and devices as well. Okay, so I'll show you what we can do with it. So first thing is we basically studied the impact of accuracy of density functional theory in terms of which exchange correlation functional you use. And if you use LDA, we have to use basically negative pressure to compensate for the error in the lattice constant. But beautifully, you will see for barium titanate, we reproduce the experimental phase transition from cubic to tetragonal to orthorhombic to rhomboidal phases as you lower the temperature. Yeah, but the TCs are grossly underestimated by 25 to 50% with respect to experiment. And this is in spite of sort of fudging for the lattice constant. So DFT is good, but of course it has some limitations. Next, we will show you that we do the coarse graining in real space domain and derive Landau functional, and that allows us to sort of again reproduce the phase transition. So these are free energies changes with respect to cubic phase. The zero line is the cubic phase, and you will see we get the sequence of phase transition from cubic to tetragonal to orthorhombic to rhomboidal. Clearly, these are first order phase transitions, absolutely consistent with experiment, and we even have access to the free energy differences. And using this, we can develop a Landau theory, and that allows us to tell what is the origin of first order character of the phase transition. And what we show conclusively is it's the quartic term of Landau free energy function, this coefficient, which is negative, and that causes the first order phase transition. Otherwise, you know, in the standard Landau theory, usually the third order term, which is allowed, if it is allowed by symmetry, is responsible for first order transition. And that's why in this case, it's actually called as the fluctuation driven first order phase transition. So once we have simulated phase transitions, we also have access to domain walls, which are very important for technological applications, because when you make devices or memories, you basically want to be able to switch the direction of polarization. So we simulated device or domain walls in these two oxides, and look at this, what a contrast between barium and lead titanate. In barium titanate, you have this 180-degree domain wall where the polarization is in opposite direction in adjacent domains, whereas in lead titanate, the domain walls are 90 degrees type of orientation, and 180-degree domain walls are much more expensive than the 90-degree domain walls. And you see, this is also, of course, consistent with what is observed experimentally. I'm not bringing in experimental details here, but you know, this demonstrates that using combination of first principles, calculations, and modeling, we are able to predict not only phase transitions, structural phase transitions, but also inhomogeneous ordering and domain wall structure of these interesting functional oxides. So to summarize this part of my presentation, what we showed, again, I didn't go into those details, is the fundamental coupling here is the coupling between strain and polarization, which is what is responsible for piezoelectricity, by the way, because the electric field causes strain in piezoelectric effect. And this coupling is responsible for first order transition, and also it is weak in barium titanate, and that's why you get a very different behavior of domain walls, whereas it's very strong in lead titanate, and you get 90-degree domain walls which are stable, and of course cubic only one phase transition. At this stage, I will also summarize that there are limitations of this approach. Basically, we had to work at negative pressure to get reasonable TCs. And this is because there are errors in bond length from LDA DFT, and also there are errors in developing the model, that process that I described to you, called coarse graining process. So recently there was a work we were also involved in testing. There is a new density functional which was developed called SCAN meta GGA. SCAN stands for strongly constrained appropriately normed generalized gradient approximation, and it means the exchange correlation energy of electron is also a functional of kinetic energy of those electrons. It's sort of a unified theory of energy functional of various types of chemical bonds, from weak bonds like hydrogen bonds of 1 millieV to stronger bonds like ionic or covalent bonds of 10 eV. So with this approach, it's possible to study hybrid systems, and that's why I'm introducing here, particularly in molecular materials where weak bonding can also be crucial. This is one approach I would recommend, is quite powerful. And we demonstrated in this paper, it works very well for H2O clusters. You see the energy that this approach gives is comparable to the most accurate energies available based on couple cluster approximation. In strongly bonded system, this energy functional reproduces the result energy difference between diamond and beta-tin structure of silicon, which is strongly bonded system, which matches almost the exact results obtained from diffusion Monte Carlo. And in oxides, what we demonstrated is the lattice constants are basically agreement with experiment. So bond length errors are eliminated now with this functional. So we were of course curious if we can use this new functional in study of ferroelectric phase transitions. And indeed, what we get is you get reasonably good TCs even without using negative pressure, as was necessary in LDA. But the errors remain. The TCs are still underestimated by about 10%. Okay, so some DFT errors are still prevailing. And then one asks the question, is the rest of the errors due to coarse graining? Coarse graining meaning we are eliminating this high energy phonons. So they can couple unharmonically with unstable phonons. And we calculated those corrections, and we find even better estimates in TC, like 10% corrections to the model that we developed. Okay, so this is sort of the state of the art. And based on that work, basically Roberto Carr wrote a news and views article in Nature Chemistry called Fixing Jacob's Ladder, that ideally you would like heavenly accuracy of calculations. And you know, this is the ladder at which standard DFT, LDA, GGA is sort of below the heavenly mark. But with this SCAN meta GGA function, we are almost getting the accuracy of highly non-local and exact functionals at the cost of semi-local functionals. So this looks like a promising approach and worth trying in molecular systems where weaker bonding is sort of commonly seen. So of course, we didn't stop here. We also have recently used machine learning ideas, basically concept of crystal graph convolutional neural networks, where basically we can work with all atoms model, meaning we don't have to derive model Hamiltonian by coarse graining, where we generate lots of structures from first principles and learn from the CGCNN machine learning model. And then that energy landscape is used in simulating phase transition. And this is very efficient because the computational scaling of this approach is order n, which opens up lots of possibilities. And then we applied this approach for epitaxial barium titanate films, and we reproduce sort of experimentally seen phase transitions from tetragonal to orthorhombic phases. So this is sort of the new development we are involved in, basically using machine learning to predict phase transition behavior, but by basically modeling DFT energies. So accuracy of these techniques will be same as what we can achieve within density functional theory. Okay, so let me now switch to the second topic of my talk, specifically martensitic phase transformation, and with the example of nickel titanium, which is a shape memory alloy. So let me first tell you what is shape memory effect, which is absolutely fascinating. You know, you will not believe that this actually happens in practice. So suppose I have a straight wire of a shape memory alloy. I deform it like this. I'm showing a gentle deformation here. And then if I release it, it remains in that shape. But if I heat up this wire, you see at high temperature, it comes back to its original shape like this. Okay. And this is called shape memory effect. And this is exactly what is used in cardiovascular stents, where this stent, which is a sort of spring-like object, is crumpled into a point particle, which is inserted through angioplasty and inserted in a blood vessel. And then by heating it with laser, it remembers its original shape and comes back to this shape of the cardiovascular stent. So these are fascinating materials, and you will wonder what is causing this very important functionality in shape memory alloys. Yeah. So fundamental to this shape memory effect is also a structural phase transition. And I introduced to you earlier, it's a martensitic phase transition from cubic B2 phase called austenite phase to martensite B19 prime phase in nickel titanium. You will see this phase transition involves cell doubling, meaning the unit cell of the cubic phase doubles here in the low temperature phase, and also large shear strains. So how do we understand this phase transition and develop a model for it? So again, just like in barium titanate, we start with phonon dispersion of the B2 phase, which is the high temperature phase. And as you expect, it has unstable modes. But unlike barium titanate, it doesn't have so many unstable modes. Most of the unstable modes of B2 phase are at M point of the Brillouin zone. M point is basically zone boundary point, which means the phonons, these phonons will lead to cell doubling if you freeze in the double well energy function. So this is the phonon which is unstable, which involves displacements of nickel and titanium against each other. And then there's other phonons, and natural question is, are they important? Yeah. If there's only these phonons which are unstable, do we really need to worry about these other modes in the system? And what we find is, unfortunately, yes, this is fairly complicated phase transition, and we have to include all of these phonons, because if you include only the unstable phonon, you get orthorhombic phase at low phase, B19 phase, which is not the martensitic phase in nickel titanium. So only if you include combination of 3 distinct phonons, some of them are stable phonons. You see, these are called the secondary order parameters of the phase transition, and include monoclinic distortion, you can get the right symmetry of the martensitic phase. So this is an example of a phase transition where many phonons are involved, although there was only one specific unstable phonon. Yeah, and these phonons are very sensitive to the strain. If you apply hydrostatic strain or uniaxial strain or shear strain, the frequencies change rapidly, and that's what is the coupling between strain and phonons which are relevant to this phase transition. So based on this, we develop a model effective Hamiltonian. Again, I will skip all the mathematical details, but basically this model Hamiltonian captures the lattice unharmonicity of phonons, of strain, basically nonlinear elasticity, and the coupling between phonons and strain, which is also nonlinear coupling. Yeah. And then using this model Hamiltonian in Monte Carlo simulations, we can predict phase transition behavior of these systems. And you will see, unlike barium titanate, these phase transitions are quite sharp. You see at the transition temperature, the strain, this is basically the ABC parameters, they change suddenly at the phase transition, and there's a hysteresis which reflects the first order character of this phase transition. And this is the M5 prime phonon, cell doubling phonon. It also discontinuously switches to its low temperature phase. If you look at the phonon frequencies of the M5 prime phonon, you will see there is a softening of phonon at the phase transition. Again, the cartoon picture, if you remember, I introduced at the beginning of my talk. That's exactly what we see in this realistic phase transition simulation. And then that phonon, I would have gone down below 0, but because the B19 prime phase stabilizes, it gets, you have stable phonons with lower symmetry structure. Okay, so indeed, TM is greatly underestimated. It's 50% of the experimental value, and we didn't know at that time what could be the origin of this error. So We looked at pressure dependence of phase transition. See, this is again a luxury of the simulation techniques. We can look at phase transitions, how they change with pressure, both negative and positive pressure. And we see that you can change the nature of the phase transition itself by stabilizing another phase between the high temperature and low temperature martensitic phases. So indeed, these phase transitions are sensitive to pressure, but the TC was 40% underestimated. So we looked at way of correcting it, and basically what we did is to include configurational entropy associated with several local minima of the martensitic phase. And using certain approximations, we show that TC actually is much higher than what Monte Carlo simulation gives, and that is much closer to experiments, but still there is underestimation of the transition temperature. Okay, so I'll summarize this part. We demonstrated that the same modeling strategy can be used very effectively in understanding martensitic phase transitions in shape memory alloys. This is a high temperature shape memory alloy, and this is room temperature. And the TCs are underestimated, and pressure is, the phase transitions are very sensitive to pressure. So I think I do have time. Pradeep or Amod, please do let me know when I'm 10 minutes from the end of my.
Okay.
Thank you. So the third example I wish to offer you is an example where phonons and spins of a magnetic ion strongly couple with each other, giving rise to a very giant magnetoelastic effect at antiferromagnetic phase transition called Nile phase transition. And this is an YMNO3. It's an interesting material. At fairly high temperatures, below to 1270 Kelvin, it becomes ferroelectric. It's an improper ferroelectric. I won't go into those details, but this involves self-rippling transition. And below, as you lower the temperature, much lower temperatures at 75 Kelvin, the Nile temperature, it becomes antiferromagnetic, means the manganese spins align in a certain way, which is not parallel to each other. Yeah. And also experimentally, Sang-Chong's group in Rutgers reported giant magnetoelastic effect at the Nile temperature, which involved displacements of atoms, which are shown here by these arrows. Okay, so this was quite exciting, and I don't think it is understood how this happens, although there are two sort of very interesting papers published on this effect. So we used our approach. Again, I won't go into details of it, but it involves the same sort of steps. In this case, instead of phonons, we work with the spin on manganese side, and we consider various orientation of spins. These are called magnetic ordering with different symmetries, and calculate their energies. And then those energies are fit to the model Hamiltonian, which is spin phonon coupled model, where the phonons are also coupling in the third order with spins. Okay, and all these parameters we calculate from first principles. And then this model Hamiltonian is simulated in Monte Carlo simulations. And indeed, in this case, we were very successful. The Nile temperature experimentally is 75 Kelvin. Our simulations give about 91 Kelvin. We find it's a second order transitions with specific magnetic ordering, which is in agreement with experiment. Even more challenging was the magnetic susceptibility curves. And indeed, we get agreement with experiment reasonably well. You see our Curie-Weiss temperature is 720 and experimental value is -700. So this is very encouraging. And in fact, just like in structural phase transition, you have phonons which are unstable. In these systems, it's the spin waves or magnetic excitations which are unstable at low temperatures in the high symmetry phase. And if you inverse the magnetic susceptibility, you will see these curves basically will drop to 0, and you will get soft modes. These are called soft spin-on modes, which again become unstable at low temperatures. And then we also simulated the domain structure in these materials. Of course, the domains are very rich. In fact, domain structure in ferroelectric and ferromagnetic materials have been studied very extensively, but not quite so in antiferromagnetic domains. So these are some of the first simulations with realistic domain structure is simulated. And you will see the domain walls are quite wide, about few nanometers. and spins rotate by 60 degrees when you go across a domain wall. And that's what these L prime are different ordered states of the magnetic spins of manganese atom. And this being ferroelectric, it also has the electric dipole polarization, which flips from one domain to another. So you have both structural domain and antiferromagnetic domain when you go across this domain wall. Well, what is more fascinating is these domain walls involve magnetic spin structure, which is totally different than the domain wall with respect to what is present in the bulk. So this is bulk magnetic ordering on the two sides. And at the domain wall, you will see you have a vertex-like magnetic spin ordering. Yeah, and that is very interesting. It means the local crystalline symmetry here, in fact, the double group of this symmetry is different from what is at the domain, bulk domain. Of course, that's not surprising because at the domain wall, naturally, you will have lower symmetry often. But in this case, the symmetry of the domain wall is corresponding to the gamma 1 representation, which means you can have trilinear coupling like magnetoelectric coupling, which involves coupling between electric field and magnetic field and this toroidal order of spins. So this is a theoretical prediction that indeed you will have transverse linear magnetoelectric effect at the domain wall. And that's something that will be measurable using piezo force microscopy. So if you take a piezo force tip microscopy tip across the domain wall, you should see interesting changes in magnetic moment and electric dipoles too. So to summarize, in yttrium manganite, we sort of predicted these transition temperatures, which are very reasonable agreement with experiment. We could also reproduce magnetoelastic effect, but we find it is much weaker than what experiments have shown. And the linear magnetoelectric coupling at this is a prediction, and that yet to be verified experimentally. So the last topic I'll cover, because I think I'll leave some time for discussion, is metal organic framework, which are sort of closer to the molecular materials, which may be more interesting to the audience here. And in this case, we are looking at a specific MOF called MOF5. And you see, what we find is the pristine structure of MOF5, if you compress it using hydrostatic pressure, it changes its crystal structure internally, because it's a porous structure and atoms inside this which will naturally respond to the applied pressure. But what is fascinating about MOF5 is it very rapidly amorphizes even for tens of kilobars of pressure. Okay, and that is a puzzle. On the one hand, you would expect MOF to be a very flexible material, but experimentally it is known that for very small pressures, it becomes amorphous. So what we did is, again, the theory which we applied to crystal transition. We look at the phonon dispersion of MOF5, and you see it's a beautifully stable structure. There are no unstable phonons. But as soon as you compress it by even 0.3%, this is hydrostatic strain, you will see many phonons become unstable here, as shown in this part. These are below zero. And these unstable phonons form flat bands. Flat bands is another very sort of emerging idea in physics of condensed matter. What it means is, since the eigenvalues of all these modes are roughly the same, any linear combination of those modes are also eigenvectors of the system, vibrational eigenmodes. So you can basically have highly localized distortions in the crystal, and they can be random. So these flat unstable modes allow this crystal to deform in sort of random way in different local regions, and that gives rise to amorphous phase. Basically, that's what we showed in this paper published just last year in JPCC. So this, of course, affects functionality, meaning there's a great reduction in porosity, which is very important to application of metal organic frameworks. So this is something similar we have shown in ZIF8, another sort of prototypical MOF structure, but there the pressures are a little higher than what are involved in MOF5. Okay, so Amol, how much time do I have? I can stop here or I can cover one last thing.
Yeah, it is 13 minutes left for discussion. Maybe you have 3 more minutes, maybe.
3 more minutes, okay. All right, then I think I'll just cover this last bit in 3 minutes and stop. Yeah, so these are again the relatively new type of materials called high entropy alloys. And these are alloys where you have more than 4 elements of equal composition. And what is believed is that this sort of condition, you have very high entropy of mixing, which stabilizes these alloys. This is in contrast to alloying, traditional alloying, where you start with, say, aluminum and put a little bit of another element. Here it's like you have 4 different or 5 different elements with roughly the same concentration. And because the chemistry of each atom can be different, size can be different, they lead to large internal lattice distortions, and of course involves sluggish diffusion kinetics, which stabilizes their single phase structure. And there's something called cocktail effect, which gives rise to amazing mechanical properties of these materials. Of course, what is open still is it's not clear which entropy stabilizes this structure and what is the ILD, which is relevant to the structure. ILD means the internal lattice distortion. So what is another challenging problem in these systems is due to large internal lattice distortion, the structure determination is quite tricky. Well, experimentally, it may not be so tricky, but theoretically, you will see it's quite challenging. And how to characterize the structural transition becomes even harder. So what we decided to do is to understand the origin of ILD and then link it to the structural transition. So first, what we show is indeed entropy is large for these alloys. In this case, we are looking at 4-component alloy. And however, the configurational entropy peaks at the equal concentration. The vibrational entropy is the dominant contribution to entropy, and that peaks just before that, and that's what stabilizes. This is the free energy, and you see the total energy is positive, means these alloys are not energetically favored, but only if you include entropy, you get free energy stabilization of these interesting random systems. Then we looked at composition dependent phase transition. If you increase the concentration of niobium in this high entropy alloy, we reproduce HCP to BCC phase transition, and the characterization was quite tricky. So there we use the concept of bond orientational order parameters, which are used in glassy systems, and also Voronoi analysis, which is used in amorphous system studies of amorphous systems. And from this we infer sort of the crystalline lattice governing that. And very interestingly, we find that internal lattice distortions peak at this phase transition composition. Okay, and that's linked with the average valence, number of valence electrons. To summarize all the parts of my talk, I sort of highlighted that there is a coarse-graining modeling scheme we have, which allows us to start from first principles and predict structural phase transitions. And I also presented to you the limitations and successes of such theories, showed that there's new development in density functional theory called scan meta GGA, may be quite accurate for a number of problems. We can't claim it's accurate for all, but it's worth looking at. And finally, I sort of highlighted these 4 transitions in crystals and showed how these govern the functional properties of these crystals. And I hope these ideas, how structural transitions govern functionality, can also be translated into molecular structures and materials. And in that sense, this should be useful. I acknowledge my group members, the PhD students who also now moved on to other places, some of them, and 3 groups, one from Japan, one from Korea, and one from Rutgers University. Thank you for your attention, and I'll be happy to have interactions.
Umesh, that was a fantastic talk, lots of possibilities, and particularly for a molecular materials community. Although you didn't really get to those materials, that's for discussion, and that's probably for one's imagination. So let me just begin by asking one question and leave it open for others. You said even in systems when there is very weak interactions, it is possible today to understand structural phase transitions and possibly what it will lead to functional changes.
Yes.
one of the systems wherein a large number of phases exist with weak interactions would be that ultimately maybe something like ice, with all these diverse varieties that are now known, about 19 phases, and some of them ferroelectric and things of this kind. So my question is it possible to really predict even such complex molecular solids today?
Yeah, so very excellent question, Pradeep. I really think something we should look at. And look at, here is the sort of some just convincing evidence that it may be effective, this new functional. You can see the screen, right?
Yes, yes.
So here we looked at relative energies of water clusters, and they of course involve the kind of interactions which govern the phase transitions you are referring to in ice. And you will see the accuracy of the scan meta GGA functional is almost overlapping in terms of energetics with the CCSD approach, the couple cluster type of calculation. So I can't be sure, because I must also at the same time admit that scan meta GGA functional doesn't describe metallic bonding as well as one would like. Metallic meaning, let's say, titanium or those transition metals. But indeed, it seems to be quite accurate in this system. So I would be quite interested in looking at these and collaborate. In fact, that's the idea of this talks.
Great. The second thing, of course, there are others in the audience here who look at nanoparticles, nanoclusters, and magnetism in these and transitions around that. So your talk pointed up, to the possibility of even predicting such transitions in molecular solids of this kind, where there is a small metallic core and then there is a ligand shell. I leave that to others probably to think about. Let me ask Thomas to ask his question.
Yes, thank you very much. Umesh, I've always thought of transitions as a very advanced topic with lots of challenges. I have a question. Can you, when addressing transitions in all these materials that are periodic, can you somehow cover defects, and to what extent defects in these structures can influence the difference between maybe sometimes those experimental results and computationally obtained results? And yeah, so if you could comment generally on imperfections and defects, and somehow how to address these sometimes sort of randomly distributed things within the structure computationally.
Sure. Excellent question, Thomas. So we did attempt studying effect of oxygen vacancies in ferroelectric transitions in this barium and lead titanate. And it is successful in a sort of limited way, I must admit, because we are able to do capture the randomness associated with the distribution of these defects, their concentration, because the simulation is quite inexpensive computationally once you have a model Hamiltonian. Okay, but the vacancy itself is a complex defect in these oxides. And the way we treat it is in a relatively simplified manner. In, say, ferroelectrics, vacancy gives rise to a local electric field, and that sort of impacts the local ordering of electric dipoles in the neighborhood of that vacancy. So we simulated vacancy. In fact, we simulated lead oxygen pair vacancies, which are common in these systems, as a dipole, local large electric dipole, and then studied the effects. But these are lattice models finally. So the effect of defects will be brought in a sort of modeling simplified manner. Yeah. Now in shape memory alloys, these defects are very important. These are these are planar defects which are quite common, like twin boundaries, which are very crucial to the shape memory behavior of those alloys. And in fact, that's linked with our underestimation of TC, Thomas. in these systems. Okay, so indeed, in comparison with experiment in the context of martensity structural transition is plagued by the fact that we don't have all the defects captured in our low temperature phases, structural defects in this case. So
Thank you.
it is in the infancy, and it's certainly something to think about and study carefully in a systematic way.
Thank you. Thank you for your comments. Thank you.
All right, colleagues, are there other comments?
Yeah, so I just wanted to ask a couple of simple questions. These metal organo frameworks, when you apply pressure, they collapse, probably giving rise to amorphous material. Is it reversible? Can you predict that in your theoretical, in your model?
Okay. So my answer is, at the moment we don't have that capability. Meaning, what we did do, Professor Rao, is we simulated another structural phase transition in MOF, which was one crystalline phase to another crystalline phase with pressure, and that of course is reversible. Yeah. But amorphous phase we haven't demonstrated yet whether it's reversible yet. Yeah, but that's of course an important problem, and we don't have that yet.
Yeah, possibly it may not be possible. Energetically, it may not be favorable. That's what I'm imagining.
Yeah, see, the difficulty I can see is these simulations which I showed for MOFs are low temperature, meaning zero temperature simulation. Where, you know, if there is a barrier between the disordered amorphous structure and the crystalline MOF structure, there is no opportunity for the simulation to cross that barrier. But if we do temperature dependence, then I would be more sort of expectant of the fact that we may be able to recover reversibility there. You know, if there is a path which connects amorphous structure back to the crystalline phase, and the barriers can be crossed with the temperature that we use.
And the reason why I asked this question is, you know, people are actually making these MOFs and then modifying them, applying pressures, applying heat treatments, and then making different materials and then using them for different applications. This is seems to be the case. The people are now, experimentalists are very fascinated about these applications.
Yes.
And the second question is, so you have applied your model, the scan model, what we have discussed now here, to alloys, basically, high entropy alloys.
There are other. Yeah. So go ahead. Yes.
There are other. No, high entropy oxides are also now interesting materials. A lot of applications are now, you know, are pouring in the literature. Particularly in energy-related applications. Is your theory can look at those?
Most certainly. Yeah, see, the high entropy alloys is again challenging problem, and what we did is, you know, again sort of what is possible within our computational resources. But certainly the same thing we can do for oxides. The cost of computation may be slightly marginally higher because you have additional oxygen atoms, and probably in these alloys it's the cation which is multiple elements, or that's what I would expect.
Yeah, so, multiple elements. Yeah, actually, so, sometimes they also look at vacancies in these sure. high entropy oxides. That is seem to be very interesting property for certain applications.
Thank you for pointing out. That's certainly interesting to us, and it should be exciting to look at.
Good. Suraj, you have you showed
yes.
your.
Thank you very much.
Can I go? Can I ask a question?
Please.
Go ahead.
Sir, very interesting talk. So I have one question related to the scan functional. So we have also employed the scan functional for the metal oxides, and we found that they reproduce the experimental structural parameters like lattice parameters quite good. And I'm not aware of how much it will be accurate in terms of the energy. For example, the one which you show a very low energy barrier for the transitions.
Yes. Okay.
How good it will be for the energy barrier side.
No, so we did show that in ferroelectric oxides, they capture energy variance better than LDA and GGA in terms of their ability to capture experimental TCs. Yeah. But I also at the same time share with you that we haven't been very successful in using it for metallic systems, metallic transition metals particularly.
Sir, can you have any comment on, let's say, instead of GGA plus a dispersion corrected one, let's say Waghmare dispersion corrected one, and the scan functional, how they are basically reproducing the data. So our experience is that PB plus D3 when we use for metal oxide, the experimental behavior is mimicked by the PB plus D3, GGA plus D3, though not as accurate as CAN. So I'm thinking that if CAN, from my experience, it is computationally more expensive compared to a PB plus D3. So if you have any.
Yeah, Suraj, so it's good to hear what you found. And what it suggests is if you want, you can first do the initial relaxation structure determination using GGA plus D3, and then later switch to scan meta GGA, where the final refined calculations, which are selective ones in a few of them, can be done with this, where you have access to more accurate electron density and energetics.
Okay. Yeah, what I was wondering is in this kind of case where you need to try large number of structures, sure, whether going with a PB plus D3 will be computationally more feasible.
Yes, it will be. But if I were you and I want more sort of confirmed results, in terms of reliable results, I would pick at least some of them randomly and do the scan meta GGA to see whether energies are reliable or not.
Sure.
That's it.
So one more thing regarding the systems which are having defects.
Yes.
So when we see such, for example, the materials which are used in metal oxides used in batteries, such kind of systems. So so we will be seeing that basically during the delithiation process or in such cases, the vacancies will be created. And at the same time, the transition metal oxidation state will change. Sure. Now their magnetic character is going to be different. The moment distribution will be different. So the kind of Hamiltonian which we have taken care in your system. So that kind of things can be accounted or.
Yeah. So see, if you already have a model Hamiltonian, which is obtained after coarse graining, then there is not much one can change, right, at the oxidation state level. But you could include effects of those changes in a model form, like a simplified model effects in the model Hamiltonian. But coming back to your question, so in fact, you must be familiar, even lithium cobalt oxide, where you often study it with lithium vacancies, and there are changes in oxidation state of cobalt. You in principle have to change even the Hubbard U parameter, which is used for cobalt. And there is no simple way in which you can predict what should be the right U parameters. So this is an open issue. What I would say is you can still use density functional theory as a interatomic potential, which gives you reasonable energies, but you have to be with vigilant eyes to see if there are any gross violations or sort of intuitive physics or chemistry is violated, and then do more refined job at those configurations.
All right. Thank you. Well, so I think probably we should close it because it's 7:36. Umesh, it has been a wonderful, tour.
Thank you. It's my pleasure.
Yeah, diverse areas of wherein new science is possible, and obviously our team is very much excited to pursue these areas using two kinds of materials. One is atomically precise cluster systems, and second is solids such as ice, molecular solids.
That's exciting. Yeah.
And the good thing is that today, many of these, their atomic arrangements and all that can be seen with aberration corrected microscopy, and many of these are available with almost all the research teams participating in this. The new possibilities are arising, and your lecture pointed at the diverse possibilities with which greater understanding is feasible
Thank you.
across the world. And this group is really collecting people from across the world in all continents. That's great.
Excellent.
Thank you, Umesh.
Thank you all for your attention.
Thank you all. Thank you all.
Thank you. Thank you.
sir.
Goodbye.
Bye-bye.
Bye-bye.
See you next month.
Thank you.
Bye.